Thanks for the introduction. My name is Quinn. I'm a PhD candidate at University of Wisconsin-Madison. I'm excited to be here today to tell you about our work optimizing security protocols for storage. So to start, it's no secret that protecting the integrity of data stored on the cloud is an important element of cloud security. But unfortunately, integrity comes at a cost. To give you a concrete example, this graph shows the cost of integrity in practice. So it compares VM Verity, which is a device mapper target in the Linux kernel that implements state-of-the-art integrity protections against two baselines. We have a disk with no encryption, no integrity protection, and a disk with encryption but no integrity protection. So the y-axis is throughput, x-axis capacity. The general trend that we see is that throughput decreases with respect to capacity. A 4 terabyte disk sees about a 75% loss, and even a small 16 megabyte disk sees about a 50% throughput loss. So the takeaway is that the cost of providing integrity can become prohibitive. Our work addresses this performance problem by developing optimized integrity data structures that adapt to workload patterns, that exploit workload patterns to reduce integrity costs. We tackle this by answering 3 research questions. The first, what is the root cause of integrity overheads? The second, in an ideal world, can we model an optimal integrity data structure? And I'll say more about what that means later. And the third, if so, can we realize the optimal or approximate it in a real system? To foreshadow a bit, the answers are here, right? The root cause is hashing costs. We can construct an optimal if we have some a priori knowledge, and we can approximate the optimal by learning from workload patterns. But let's start with some background. Suppose you have a typical infrastructure as a service deployment where you provision a virtual machine, you run an application inside of it, and the application requires some access to some fast local storage. So the application communicates with the file system through system calls, which translates those into a series of block operations handled by the block layer. In this scenario, if an attacker manages to gain control of the storage device or the storage interface broadly, then they can inject bad data into the VM and compromise the integrity of the system. In practice, the way that we prevent this kind of attack is by adding a security layer at the I/O interface that performs some integrity checks before you return any data or acknowledgement up the call stack. The security layer handles 2 high-level routines, update and verify. So whenever you write a block to the disk, you push the data out to the disk, and you update some associated security metadata. And whenever you read data, you check that the data is consistent with the associated security metadata. Informally, this is known as a cryptographic proof system. Now let's unpack this a bit more. The security metadata itself is composed of 2 things. We have message authentication codes, or MACs, and Merkle hash trees. MACs give us an authenticity guarantee that any data you read off of the disk is legitimate data that you put there. And Merkle trees give us a freshness guarantee that any data you read off of the disk is not only legitimate, but is also the latest version of data that you put there. So to be more precise about what we mean when we're reading and writing blocks, if we come back to the security layer, when we write a block, first we compute a new block MAC, and then we update the Merkle tree using that MAC. When we read a block, we check that the MAC is consistent against the data, like we would any other checksum, and then we verify the MAC in the Merkle tree for freshness. Now the Merkle tree works as follows. The MACs of the data blocks are the leaves in the tree, and the process of updating or verifying a MAC involves recursively fetching sibling nodes, concatenating them, and hashing them at each level in the tree until you get to a single root. The root's typically stored on chip or sealed in a TPM and is out of control of the attacker. So for an update, you go through this recursive process, generate a new root, and save it. And for a verify, you do the same thing, but you compare a computed root against a known good root. And so the guarantee that you get is that whenever you read some data, if an attacker tries to inject stale or otherwise invalid data into the VM, then the integrity check would fail. Now, in the paper, we provided an analysis showing that the time spent computing hashes during this recursive process dominates the time spent simply doing a data access on a fast disk. So we measured it to be about 200 to 300 microseconds doing an update or verification versus doing a data access can be on the order of tens of microseconds, depending on what kind of disk you use. So we concluded that hashing is the bottleneck, and to reduce overheads, we need to reduce hashing costs. The key insight in our paper is that there's an opportunity to reduce hashing costs by exploiting reference locality. It's known that storage workloads often exhibit a high degree of reference locality, where a small number of blocks is accessed most of the time. So our idea is that we can exploit this by breaking away from a balanced tree structure, allowing the tree to become unbalanced, and keeping the max that are associated with hot blocks closer to the root. So the result is this tree structure where max associated with hot data have shorter update and verification paths, which means less number of hashes and therefore lower hashing costs for both frequently accessed data and overall in general. Now, the intuition is simple, and so this raises the question, why now and what were we doing before? Well, prior works largely focused on offline integrity checking, where performance was not a primary concern, and so using a balanced tree was sufficient to meet their needs. In our case, we assume the application's running inside of a confidential virtual machine, right, a cloud VM, and requires real-time integrity checks as the application's reading and writing data from the disk. Now, more importantly, we're only beginning to become aware of the fact that hashing is a bottleneck because emerging storage devices have very low data access latencies, right? And so the ratio of time spent computing hashes versus doing a data access is only growing, right? Growing substantially. So our work builds on this new idea of using an unbalanced tree structure in two parts. First, we recognize that achieving a minimum hashing cost is ideal. So we first develop a definition of an optimal hash tree structure. And then we design a heuristic approach that addresses some of the limitations of the optimal definition. So we provide the reduction and the full technical details in the paper, but at a high level, we define the optimal by tying it to a parallel problem in compression. In compression, prefix trees are used to map a set of symbols onto code words. Encoding process works by traversing a path down to a leaf in the tree and appending either a 0-bit or 1-bit to the code word bit string, depending on which direction you move during traversal. The goal is to find an encoding that produces a minimal representation of some original data. And so the guarantee that we get when we construct an optimal prefix tree with an algorithm like Huffman encoding is a tree structure where hot symbols are assigned shorter code words. So in this example on the right, symbol B3 occurs 30% of the time, it is encoded with 2 bits, while B7 occurs 5% of the time, is encoded with 4 bits. So we modeled the leaves in the hash tree in the same way because it gave us a very clear guarantee, which is that max and/or their associated blocks that are accessed more frequently will be placed higher in the tree, right? Leads to shorter update verification paths and therefore lower hashing costs. Now, a condition of building an optimal tree in this way is that you need some knowledge about the workload ahead of time. You need to know the probabilities so that you can construct the tree. This is a limitation because it's rarely feasible to have that kind of knowledge in practice. Now, the optimal is still useful as an evaluation tool because if you do have that knowledge, then you can construct the tree, and that allows you to establish an upper bound on performance, right? Maximum throughput, minimum overhead. In the paper, we call this the optimal tree oracle. Ideally, in a real system, we want to move away from this assumption, though. So in our second contribution, we approach this by drawing a connection to a data structure that's widely used for tasks like garbage collection and IP routing lookup, display trees. We designed an adaptation of display trees called Dynamic Merkle Trees, or DMTs, that are tailored to our use case of a hash tree. The key mechanism that drives display tree is that whenever you access a leaf in the tree, you perform a series of rotations to move the node all the way up to the root, or at least part of the way there. And so over time, you end up with this tree structure where hot data tends to accumulate higher in the tree and cold data tends to fall lower in the tree. Now, there are several desirable properties of display trees that made them a good candidate data structure to build the DMTs from. To summarize, display trees are inherently unbalanced tree structures. Unlike the optimal, they require no knowledge about the workload ahead of time. Right? We can start from any initial state, and the structure of the tree will be completely driven by the workload pattern. And this adaptivity is particularly useful because it allows you to capture temporal patterns and dynamically adapt to changes in workloads over time. So while intuitively it makes sense that we should be able to exploit reference locality in this way, we had to address several challenges. The primary challenge being that doing these rotations can be costly. Right? So when display trees are used for search, rotations might be cheap because you only need to update some pointers. But in the context of a hash tree, whenever you do a rotation, you change the structure of the tree, and we need to commit that change by essentially recomputing all the hashes from the rotation point up to the root. So we need to reduce those costs. We do that by introducing two heuristic parameters. The first is display probability P, which says that rather than displaying on every access, we'll only display on a certain percentage of accesses, for example, 1% of the time. And the second is display distance D, which says that on those accesses that we do decide to display, rather than displaying the node all the way to the top of the tree, we'll only display it half of the way there, or a fourth of the way there, and so on. Together, these help to reduce costs. Now, the DMTs work in 3 steps. We attach integer hotness counters to each node to track the relative access frequencies. As the block layer begins receiving I/O requests, on the accesses that we do decide to display, we perform the rotations per the standard display rules. So looking in this figure, depending upon the arrangement of the nodes at the time of the access, it might either be a zig case, a zig-zig, or a zigzag. And finally, when we decide to display, we rotate upon parent nodes rather than the actual leaf node, and that helps us to avoid some hazards that can result from rotations. So we implemented the DMT and the optimal tree, about 5,000 lines of C++. It's a block device driver using BDUS framework. The driver intercepts read and write IOs and calls the update and verify functions before we return any data or acknowledgement of the call stack. As an optimization, we also introduce a small hash cache that allows us to avoid some metadata IO during the update and verification process. The driver runs on standard Linux systems, and we did the evaluation with EC2 instances with local NVMe disks. In the paper, we looked at a variety of different workloads, some synthetic generated with FIO, an Alibaba trace dataset, and file bench workloads. Today, I'll focus on 2 key evaluation questions. The first, can DMTs scale better with respect to capacity? And second, can they adapt quickly to workload changes? This graph compares DMT against DMVerity and several other baselines. So let's take a look at what's in the legend first. We have a disk with no encryption, no integrity, a disk with encryption, no integrity, and we also have 4, 8, and 64 array trees. And for reference, DMVerity here is a binary tree. Now, we looked at these other trees for juxtaposition. I won't say much more about them, but I'll mention that in the paper, we provided another analysis where we showed that simply using a wider tree was not sufficient to reduce hashing costs. And it's because there's some unique challenges in the context of storage level hash trees, where essentially when you use a wider tree, the actual input to the hash function is larger. And so the actual per hashing costs are larger. So they don't break even on the trade-off. Finally, we have the optimal, which we construct by recording a workload trace ahead of time and building the tree from it. So looking in the graph on the top, y-axis is throughput, x-axis capacity. The general trend that we see is that the performance of the baselines decreases with respect to capacity. Meanwhile, performance of DMTs remains about constant. And in fact, we see that DMTs consistently provide about 85% of the optimal throughput. And this is precisely the scalability guarantee that we were looking for. Graph on the bottom, we look at tail latency, and the key takeaway is that DMTs provide up to a 40% improvement in tail latency. So although splaying can be costly, through our design, we can reduce those costs over time. And this next experiment, this graph shows a 150-second snapshot of throughputs observed under a workload that alternates between uniform and zip VM phases. Each zip VM phase is centered on a different region of the address space. So the y-axis is throughput, x-axis time. The key takeaway is that DMTs, at the start of the zip VM phases, the DMTs can quickly adapt to capture the skewed workload pattern and provide a speed up. And during uniform phases, provide comparable performance otherwise. So the significance is that DMTs can adapt to both changes in workload shape and changes in workload regions of interest over time. To summarize, storage integrity is important but costly. Merkle tree traversals are the root cause of overheads, and we can reduce those by using optimization and designing adaptive data structures. The code's available for other researchers to use. Thank you, and I'm happy to take any questions.